Welcome back to the Deep Dive, everybody. Today, we're taking a look at something truly special. You've provided us with the source code, the actual code that helped land Apollo 11 on the moon.
The Apollo 11 code.pdf.
Yeah.
It's incredible.
Yeah, it's amazing to have this. Now, we're not going to turn you into programmers or anything like that, but what we want to do is sort of unearth some of the really fascinating details in this code, sort of give you a glimpse into the minds of the engineers that, made this impossible feat a reality.
It's really humbling, actually, to look at this raw code.
Yeah.
You really see the depth of thought and planning that went into this, every single aspect meticulously considered.
Absolutely, yeah. And I mean, just scrolling through it right now, one of the things that immediately jumps out at me is this sort of verb in the code. It's called V3D3E.
Okay.
And this essentially signaled to the Apollo guidance computer that the data from the rendezvous radar was ready to be stored. It really highlights, I think, the immense complexity.
Mm-hmm.
All these different systems on the spacecraft had to communicate and exchange critical information constantly.
Absolutely. That V3E is what they call an extended verb,
Okay.
which is fascinating in itself.
Yeah.
These were really the tools the astronauts had
Right.
to actually interact with the AGC.
Right.
It wasn't as simple as like a point-and-click interface.
Right.
This was a deliberate, very sort of, step-by-step process.
Yeah.
Using verb-noun pairs.
Yeah. Wow. And, this Apollo 11 code.pdf, it really does run the gamut. You have sections in here on extended verbs, the ones that we just talked about, orbital mechanics,
Wow.
guidance parameters, display routines, alarms, you name it. And what we're going to do is we're going to pull out some key examples that really illustrate, just how complex
It's amazing.
and the astonishing precision.
The sheer amount of work.
Yeah, that went into this, into making this software work. So you're ready to kind of get started and really dig into this a little bit.
Let's unpack it. Let's get into the extended verbs, for example.
Yeah.
So we talked about V3E,
Yeah.
but there were a whole bunch of them. So you also see things like V70 UPD, V71 UPDAT, all the way to V73 UPDAT. And what these update routines appear to do is take new information, from the systems of the spacecraft or astronaut input and actually update the computer's, internal calculation.
Gotcha. So for instance, if an astronaut entered, V70E,
Right.
that would trigger the V70 UPDAT routine.
Exactly.
Okay. And it's interesting because looking at the sort of flow of the code after this,
Yeah.
it looks like it would then often jump to V73 UPDAT +1.
Okay.
And then there's an instruction to save something called UPVE until it was safe to enter a specific program section, which is P27 in this case.
Yeah.
Do you have any idea why they would do this careful handoff? Because it seems very deliberate.
It does, and it speaks to the priority they gave to making sure the data was consistent and correct. So spaceflight, as you can imagine, is not like running a program on your computer.
Right.
It's not necessarily sequential.
Right. Yeah.
Different systems are providing data at different times. So you might have the radar sending you a new reading, while the navigation system is in the middle of a calculation.
Sure.
By saving this UPV ARB, what they're doing is they're making sure that the computer doesn't jump into a program, a critical program like P27, in the middle of receiving that information.
Right.
So it's about managing this asynchronous flow of data,
Yeah.
protecting the integrity of it all.
I see. It's kind of like, imagine you're an air traffic controller. Right?
Exactly.
You're not going to issue a landing clearance while you're still receiving, information about other planes in the airspace.
Yeah.
You're going to wait for everything to be logged, make sure that information is correct, and then you're going to issue that instruction.
Exactly. Perfect analogy.
Okay. So then we see a command called test exec. It looks like this was used to try to grab control of the display
Right.
if it was available. But if not, it would trigger an operator error.
Whoa.
So what was so important about controlling the display, and how is this, I guess, a pretty basic form of resource management?
So the display, although quite simple by today's standards, was really the computer's primary means of communication with the astronauts.
Right.
You can imagine multiple programs might want to display different data at the same time, so it's their trajectory or targeting information.
Yeah.
Test exec was a very simple but crucial mechanism to prevent, chaos, essentially. You can imagine if two programs were trying to write to the same space on the screen, it would be unreadable,
Right.
possibly dangerous. So by triggering this operator error, if the display was busy, it would alert the crew that something needed their attention,
Okay.
or that program couldn't proceed. And you'll often see, actually, as well, UPO mentioned quite a bit, which is a common exit point for these update programs.
Okay.
So kind of a way to finish up cleanly and move on.
So, we see things like UPF and DVAC and FindVac, which looks like it's all about finding a VAC. You talked about memory before. So is VAC kind of like a specific location within the computer's very limited memory?
You're exactly right. You can think of it as like a small temporary workspace
Okay.
within the AGC's memory.
Yeah.
And remember, this is a real-time system.
Right.
So the computer has to react very quickly to things that are happening. So maybe it's a sensor that's sending a signal, an astronaut's pressing a button. And these are often handled through interrupts. So the computer essentially has to pause what it's doing, deal with the interrupts, and then go back to what it was doing before.
Gotcha.
FindVac would locate a free space in memory where they could temporarily save information about what they were doing before, then jump to handle that interrupt with call install, and then, importantly, make sure that they can resume exactly where they left off.
Right.
Memory was precious, so they had to be very, very efficient.
Sure. And then kind of following on from that, we have UPJOB and another call install, but with a note that this could put a job to sleep if an orbit integration was in progress.
Right.
So it seems like this is some really clever task management.
It is.
It's prioritizing those really critical calculations.
Exactly.
Like figuring out where you are in space.
Right. Orbit integration, so calculating the path of the spacecraft, is very computationally intensive, even for modern computers.
Yeah.
So you wouldn't want a less critical task sort of hogging resources and slowing it down.
Sure.
So UPJOB would check, hey, is an orbit integration in progress?
Okay.
If so, this install would basically pause a less important job.
I see.
Allow the orbit integration to run unhindered.
So it's kind of like having a priority lane on the information highway, I guess, to let the most urgent traffic through. Okay. Let's shift gears a little bit and look at some of the code involved in, guiding the spacecraft through space, specifically those orbital and trajectory calculations. One thing that I came across is this thing called moon flag.
Okay.
Any idea what the purpose of having a specific flag related to the moon was, and what kind of errors could have occurred without it?
So moon flag was probably just a simple on or off switch, a Boolean, as we call it,
Okay.
that told the software, hey, are we operating near the Earth or are we by the moon?
Right.
And that would influence all sorts of calculations. Gravity is different.
Right, of course.
Other parameters might change. Without it, the computer wouldn't know which physics to apply.
Yeah.
And that could be disastrous. Imagine using a map of, say, London when you're actually in New York.
Yeah.
It's not going to work out very well.
Right. Okay. So then there's this gamma combi that appears multiple times.
Right.
It's clearly doing some kind of computation. Any thoughts on what it might be doing?
Well, without more context, it's hard to say for sure. But judging by its repeated use, it likely calculates some important intermediate value.
Okay.
Maybe an angle, as the name GAMCOM suggests. You often see these routines used as building blocks in more complex calculations.
Okay. So let's talk about those more complex calculations, because we see alpha, beta vi, and then unit all together. This sounds like it could be related to, something called normalizing vectors, which I think is key when you're trying to determine direction in space.
Absolutely. So normalizing a vector basically means taking a quantity that has both length and direction and making that length one so all you're left with is the direction.
Gotcha.
Alpha mam and beta v might be figuring out the components of these vectors, how far they extend in each direction.
Yeah.
And then unit would perform that normalization.
Okay.
It was absolutely essential for figuring out things like the direction to a star or which way the spacecraft was pointing.
Right, right. And we see all sorts of really, fundamental math operations here, like norm, round, PDDL. I think this stands for push down double load.
Right.
And BDDV, which might be double division. This really underscores the mathematical rigor at the heart of this whole endeavor, right?
Spaceflight relies entirely on very precise math. PDDL, or push down double load, that was likely used to manage the numbers they were working with.
Okay.
Double precision calculations, so lots of decimal places to maintain accuracy. And then BDDV would do the division on these larger, more precise numbers.
Gotcha. Now, I also see TDC and Integar V2, which sound like they might be integration routines. Essentially, what I'm thinking is they were used for predicting the trajectory, figuring out where the spacecraft would be in the future based on its current motion.
Yes, that's exactly it. Predicting a spacecraft's path isn't as simple as drawing a straight line.
Right.
It involves these things called differential equations, which are all about how the position and velocity change over time.
Sure.
So integer v2 is probably one of the numerical methods they use to approximate solutions to these equations.
I see.
And then alongside that, you have DFQ, Tom,
Mhm.
which is managing these small steps in time
Gotcha.
and keeping track of all the calculations needed for this process.
Okay, and then we have VXSC being used with velocity vectors, things like VSR1, FV, ZV, YV, and a time step H. This looks like it's just a direct application of basic physics, how velocity changes over time because of acceleration.
You got it. So velocity is just how quickly your position is changing, and acceleration is how quickly your velocity is changing.
Right.
VXSC is doing this vector scalar multiply. So probably taking the acceleration vector, multiplying by this tiny time step h,
Yeah.
and that gives you the small change in velocity during that instance.
Right.
And then you add that on to the current velocity to get a slightly updated velocity.
I see.
Do that many, many times.
Yeah.
And you can predict your trajectory.
Gotcha. And finally, in this section on orbital calculations, we have GenTran for, it says general transformation.
Right.
I imagine this is for switching between all those different coordinate systems.
Yeah. Absolutely. Think about it. Even when you're describing a location on Earth, you might use GPS coordinates.
Yeah.
Or you might say, I'm 5 miles north of this landmark.
Yeah.
So in spaceflight, you need different perspectives, different frames of reference for different tasks.
Right.
So for targeting the moon, a moon-centered coordinate system makes more sense.
Right.
But for controlling the spacecraft's orientation, a system aligned with the spacecraft's body is more useful.
Yeah.
So GenTran was probably a very versatile routine to do these conversions.
Amazing.
Between different viewpoints.
Yeah, the amount of complexity that's in here is just astounding.
Yeah.
So let's talk about some of the constants and the parameters, because I see things like KPIP15 for scaling delta velocity, max V bits for maximum displayed velocity,
Right.
and even torque jet 1, which I think relates to the thrust of one of the jets.
That's right.
So these are the actual numbers
They are.
that underpin their models.
Right. Yes, they provide the specific values that the software is using to make calculations and to actually interact with the hardware.
Okay.
So KPIP15 probably scales the change in velocity to the correct units used by another part of the system.
Right.
Macro G bits would be a safety limit on the velocity that's displayed to the astronauts, so you don't get nonsensical readings.
Yeah.
And then torque jet 1 would precisely define the amount of rotational force produced by one of the jets used to orient the spacecraft.
Okay.
Very crucial for fine-tuning the attitude.
We also see parameters related to mass, like full apis, I think, for ascent, and middle MD for the minimum weight of the lunar module.
Yeah.
And even these fundamental gravitational constants, like for TMUM, which I think relates to the moon,
Right.
for TMUE for Earth,
Absolutely essential for accurate physics.
the Earth MU,
Yeah.
and then even MEM37. It seems like these were absolutely essential, so their physics models were accurate, right?
Yes, mass changes dramatically as you're burning fuel. So having those values for different mission phases was critical to calculate the trajectory and also predict the fuel consumption.
Sure, sure. And then you have the gravitational constants, which are, of course, the forces acting on the spacecraft.
Right.
So using those precise values for both Earth and the moon.
Right.
Essential
Yeah.
for navigation and maneuvers. And of course, I can't overlook moon rate,
Okay.
the angular velocity of the moon.
Right.
The precision here is astounding,
It is.
extending to many decimal places.
It highlights the need for accuracy in this mission.
Yeah,
Even a tiny error in the moon's rotation rate would accumulate over time
right.
and could lead to missing a landing site or a rendezvous point.
Yeah. So let's talk about how the spacecraft's velocity was updated in their simulations.
Okay.
We have this routine called speed run. And it looks like it takes the current acceleration, which is really just all the forces acting on the spacecraft. Right?
Yeah.
The elapsed time, dt, uses that to calculate the change in velocity. And then it adds that change to the existing velocity.
Yeah.
That seems like, to me at least, that's the core of how they simulated the spacecraft's motion.
You're exactly right. Speedrun was really the central routine for what we call propagating the spacecraft state, so basically predicting where it's going to be in the next instance.
Gotcha.
Taking that acceleration, multiplying by a small amount of time,
Yeah.
that gives you the change in velocity. Add that to the current velocity, and you
Yeah.
get the new velocity.
Gotcha.
Repeat. many, many times.
Yeah.
And you can get a nice prediction of your trajectory.
Okay, and I also see these scaling factors, like, *2 to the -5.
Right.
Or *2 to the -7.
Right.
Applied to some of the velocity components.
Yep.
And this immediately makes me think of fixed point arithmetic, which was used on the AGC.
It was.
And, required very careful handling of those numbers so they didn't get too large. So could you explain why these scaling factors were necessary?
Sure. So the Apollo guidance computer didn't have the luxury of what we call floating point numbers today.
Okay.
It used fixed point arithmetic, which is more efficient for the hardware, but means you have to be very careful about how you're representing these numbers.
Right.
So these scaling factors that you see were a way to manage the magnitude of those velocity components,
Right.
to make sure they didn't get too big or too small.
So it's kind of like, I guess if you were using a ruler that only had millimeter markings, right, you could still measure something that's, a meter long.
Yes.
But you'd have to be clever about it.
Exactly. It's about maintaining the level of accuracy you need without exceeding the limitations of the system.
Right. So let's look at some of the fundamental mathematical tools that they had available, the mathematical subroutines. We see TAD for triple precision add,
Right.
sign gene to check if a number is negative, VXSC, again for vector times scalar, deload for double precision load, VSC for vector divided by scalar, PDDL, MXV, which is matrix post multiplied by vector, and DOT for the dot product. It seems like these were just the essential building blocks for all the complex calculations, right?
They were. Those are the bread and butter of the AGC's computational capabilities.
Yeah.
Those subroutines handled all the basic arithmetic and algebra needed for everything, really.
Right.
Implementing them correctly was essential for the software's performance and reliability.
And we have various store commands like store1, store2, stodl, stovel, and stotcc. These are clearly for saving data in different formats, different locations in memory.
Yeah.
It really underscores, I guess, how carefully they had to manage the computer's limited memory.
Yes, memory was at a premium. They had to be very deliberate about how they stored information.
Right.
Those different store commands would correspond to saving, different types of data, single precision numbers, double precision vectors, and so on, into specific allocated areas of memory.
Gotcha. So I also see this this call code instruction.
Right.
And the retrieval of a 15-bit address. This sounds like the mechanism for calling subroutines, essentially jumping to reusable blocks of code and then coming back to where it left off.
Exactly. So call code was the instruction that allowed the program to execute another section of code, the subroutine, and then return back.
Okay.
So the 15-bit address would be the location of that subroutine.
Gotcha.
And that was really key to writing modular and efficient code.
And we see pre-dot and dot sub for calculating dot products.
Okay.
So why is the dot product so important when you're dealing with spacecraft motion and orientation? I think this is probably a pretty foreign concept for a lot of listeners, right?
It might be. So the dot product really tells you how much two vectors are aligned with each other.
Okay.
So mathematically, it gives you a value that's related to the length of those vectors and the angle between them.
Gotcha.
In spaceflight, this is used for all sorts of things. Finding the component of velocity, in a certain direction, or calculating the angle between the spacecraft's orientation and a target, even figuring out how much force is being applied in a specific direction. Very versatile.
Okay, and just a brief mention of some other math routines like division with ddb,
Right.
normalization, again, with norm, square roots with squared sub, and bit shifting with g-shift.
Yeah.
It really seems like they had a very comprehensive library, essentially, of math functions at their disposal.
They did, and those were fundamental for everything they needed to do.
Yeah.
Guidance, navigation, and those would have been rigorously tested to make sure they were accurate, they were efficient.
Sure.
Within the limits of the AGC hardware.
Okay, so let's move on to how the computer handled the spacecraft's orientation. Coordinate transformations and rotations. CDU trick and its variations like CDU tricks really stood out to me.
Right.
It looks like they were used to calculate the sine and cosine of angles, and then store them in specific memory locations, NCDU and CASCDU. And they did this in a specific order. First for the y-axis, then z, then x.
Okay.
So why was this trigonometric calculation so crucial for their orientation?
So you can imagine trying to describe the orientation of an object in 3D space. It gets complicated very quickly.
Yeah,
We use angles to define how much it's rotated around different axes,
right,
and sine and cosine are the tools to actually translate those angles into changes in coordinates.
right.
CDU trig was probably a routine to efficiently calculate these values for the angles coming from what we call the CDUs, coupled display units, which were the astronauts' main way of controlling the spacecraft's attitude,
I see.
and storing them in that order, Y, Z, X, will correspond to a specific sequence of rotations.
Gotcha.
These transformations were key for everything from pointing the antenna in the right direction to firing the engine.
Okay, and we also see AXSRT, which seems to be about switching between different coordinate systems,
Hmm.
the navigation base, which is NB, and the stable member, or SM. So why were these two systems important?
The navigation base, or NB frame, was likely a fixed system,
Right.
maybe aligned with the stars, an unchanging reference point,
Okay.
while the stable member frame, the SM, was tied to the spacecraft's inertial measurement unit, or IMU,
Right.
that gives you information about rotations and accelerations.
Gotcha.
Being able to convert between these two frames was critical.
Yeah.
So the guidance system needs to know the spacecraft's attitude, that's the SM frame, relative to a fixed point, that's the NB frame,
Okay.
to actually navigate and maneuver. AXSRT was the bridge between those viewpoints.
Okay, let's look at some of the guidance and control code.
Okay.
I saw plus fire and neg fire, which clearly relate to firing the jets for attitude control. So plus for one direction, minus for the other.
Right.
And then old sense to track the state of those jets.
Right.
So it's cool to see this direct interaction between the software
It is.
and the hardware.
Absolutely. Those were the commands that actually turned the guidance system's decisions
Right.
into physical actions.
Yeah.
Plus fire, neg fire, sends signals to specific thrusters
Right.
to fire for a precise duration to rotate the spacecraft.
I see.
Old Sense was probably keeping track of which jets were currently firing or had recently fired, which was important to prevent, weird oscillations.
Okay, and we also see rated B1 and drift bit, which appear to be about rate deadband and drift control.
Okay.
So could you explain to someone who's not an engineer what a rate deadband is and why it's important?
Imagine trying to hold a laser pointer perfectly still. It's impossible.
Yeah.
Your hand is going to tremble slightly. A rate deadband in the attitude control system is basically a small threshold.
Okay.
If the rotation is less than this threshold, it won't fire any jets to correct it.
Gotcha.
So that prevents the system from constantly making tiny corrections for insignificant disturbances.
Right.
Save fuel, prevents jerky movements.
Right.
And then drift bit allowed them to compensate for a very gradual but persistent drift over time.
Gotcha. And SODO, that storable load, right?
Yes.
It's being used with range and R rate.
Okay.
So calculating the distance to the target
Right.
and how quickly that distance is changing.
Exactly. Key information for rendezvous.
Yeah.
So range and range rate are fundamental when you're trying to get two spacecraft to meet up in orbit.
Right.
Guidance system uses radar or other sensors to measure that.
Yeah.
Those double precision values are critical for making accurate calculations.
Okay. And we see unit Z again, really emphasizing how important direction is in space.
It is.
And then CDU NBSM, which is a specific coordinate transformation involving the CDUs, those astronaut display units,
Right.
and the navigation-based stable member frame that we talked about earlier. So it seems like the astronauts' view of their attitude was directly linked to all these complex calculations.
CDU NBSM likely took the spacecraft's orientation from the stable member frame, transformed it into the navigation base frame, and then processed it even further to display it on the CDUs.
Gotcha.
So the astronauts could actually see the attitude relative to a fixed reference point.
So let's talk about how the system dealt with unexpected issues. Alarms and error handling. I see things like alarm TB and VAR-alarm with specific codes, for example, V05N09.
Okay.
So it's clear that the system could flag different issues, right?
Absolutely. Those were crucial for letting the astronauts know if there was a problem, and they could then take action.
And we see go flash and go to poo as potential responses to these alarms. Go to poo.
Right.
Sounds a little, I guess, a little whimsical for such a critical system.
A bit of humor, perhaps.
Yeah.
Go flash probably triggered a visual warning on the spacecraft's display.
Right.
Go to poo, well, despite the name, would have directed the software to a safe state,
Right.
depending on what the alarm was, in this case, V05N09.
Okay, so now let's look at the specific challenges of landing on the moon. I came across constants defined for velocity x, things like negative 0.6440 e negative 5 b14.
Okay.
I assume these relate to the landing radar and those
Yeah.
incredibly precise calibrations.
They do. Those constants would have been derived from rigorous testing of the lunar module's landing radar.
Right.
They provide the scaling and offsets needed to convert the raw signal from the radar into accurate velocity readings as they were approaching the surface.
Gotcha. So we also see Tetlum, which might relate to the lunar module's thermal environment,
Okay.
preset for setting some variables for the landing. And routines involving ARIT3 and VTT3, which seem to be about estimating the lunar module's position and velocity during descent.
Yes, so Tetlum could very well be related to monitoring or even compensating for temperature variations, which can affect the accuracy of sensors.
Right.
Preset would make sure that all the variables used for the landing were initialized with the right level of precision. And ACT3 and VKT3 would deal with the lunar module's position and velocity, respectively.
So then we have DZDVLVC and DLVLVC, which seem to be about handling those very precise changes in velocity during the actual landing.
Right.
And then there's this LUNSF,